This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about statics, CE 2301. We do a moment of inertia by integration problem, do it two ways, and demonstrate this sort of trick thing of how you do one of the integrals. So we've got a curve here, as shown. It has a boundary on the left side of the y-axis and on the bottom of the x-axis. So it gives us two different ways of doing it. The curve is defined as y is equal to 4 minus x squared. So the first way we're going to do this is by using a vertical strip for our differential element dA and demonstrating how to integrate that. You get the same answer no matter how either way. Okay, so when we use a little differential element y dx, we're going to look at the equation sheet. We want Ix and Iy, the moment of inertia about those x and y axes on the left and on the bottom. So to do the moment of inertia about the x-axis, the trick I'm talking about is this little thing over here I've got in blue, where we've worked out a formula for this very special case of a rectangle with an x-axis on its base. And when you've got that situation with a rectangle with dimensions b wide and h tall, then the moment of inertia about that axis, x-axis, is bh cubed over 3. So we're going to use that to simplify our analysis over here for dA by observing that it is also a rectangle with its base on the x-axis. Therefore, we're going to define dIx, the derivative of the moment of inertia with respect to x-axis, for this very special case, is bh cubed over 3. In this case, for this differential element dA, the base is dx, h is the y value along the curve, and then divide by 3. So another way it's sometimes written is 1/3 y cubed dx. So to get the moment of inertia with respect to get Ix, we're going to integrate that instead of what's on the equation sheet. Ix is going to be equal to the integral of dIx. And we just said that that's going to be the integral of 1/3 y cubed dx. Well, in this case, y is equal to 4 minus x squared. So that's going to be, we'll bring the 1/3 out of the integral. 1/3, the integral of y cubed, where I said y is equal to 4 minus x squared. And we're going to cube that, and then dx. So I plug that into my integral calculator, TI-36X Pro or something, and I'm going to integrate along the x-axis, so I'm integrating from 0 to 2. And after a few seconds, it spits out the answer, 19.51. And the units of this are inches to the 4th power. Everything's in inches, and then I've got inches cubed. And once I integrate dx, that's also inches, so I get inches to the 4th. For Iy, I want to use the equation on the equation sheet, which is that Iy is equal to the integral of x tilde squared dA. In this case, x tilde is the distance to the centroid of the differential element dA, so it's just whatever the x value is along that curve as you integrate it. So x tilde is equal to x. And so the integral becomes the integral of x squared, and then dA is y dx. And that's the integral from 0 to 2, once again, because we're integrating along the x-axis, of x squared, and y is equal to 4 minus x squared. Oops. And plug that into the integral calculator, and after a few seconds it spits out the answer 4.266 inches to the fourth. Always want to apply common sense and check that answer, see if it makes sense. Moment of inertia is proportional to the square of the height. And so because this thing is basically 4 inches tall and 2 inches wide, so the height is twice the width, then we would expect the moment of inertia to be approximately 2 squared. And so this fits those parameters basically. Ix is about 4 times bigger than Iy. So it seems to be in the ballpark. Now we're going to do it the other way, which is take a differential element dA perpendicular to the y-axis, so it's a horizontal rectangle, and its width is x and its height is dy. And this time I'm going to be integrating with respect to y along the y-axis, so I need to rearrange my equation of that line, that curve that forms that boundary of the area, as x equals 4 minus y to the 1/2 power. Now I'm also going to use this trick, or this simplification, where the moment of inertia of a rectangle with the y-axis on its side, like here in blue, is Iy is b cubed h over 3. So we want to develop a way to say diy in this case is b cubed h over 3. Well, b is x, so it's going to be x cubed. H is dy, and then divide by 3. Rearrange that and just call it very similar to that other one, 1/3 x cubed dy. So now we're going to integrate, let's do Iy first, by integrating diy, which we just said is the integral of 1/3 x cubed dy. Plug in what we've got for this case, which is bring the 1/3 out of the integral. X cubed is 4 minus y to the 1/2 power. Then I need to cube that because I've got x cubed, and then I've got dy. I'm going to integrate now with respect to the y-axis, so I want to go from 0 to 4 in the y direction. Plug that into my integral calculator, and once again I get that same answer, 4.266 inches to the fourth. So now Ix, I'm going to use the equation sheet, which says that Ix is equal to y tilde squared dA. Well, for any differential element, y tilde is just equal to y, wherever it is on the curve. So this becomes the integral of y squared dA, and dA is x dy. So for this case, I have the integral of y squared times x is equal to 4 minus y to the 1/2 power dy. Plug that into the integral calculator, and I get that same thing, 19.51 inches to the fourth. So you see, it's just two different methods using a vertical strip and a horizontal strip, and that little trick of the little differential DIX or DIY, depending on which strip you're using.